Hello guys, welcome back to my channel, and today we'll be doing another innocent looking integral. So let's get to it, let's go on the journey together. So our problem is, let's call that I. It's defined as the integral from 0 to pi over 2 of x divided by sine of x and a dx. Now again, looking at the integrand, say our integrand was something like sine of x over x, then we could have done we could have used the Leibniz rule, but it's not, so let's forget that. We have a singleton x and we have a sine x, so we could actually do integration by parts, and I can assure you that you're going on the right direction. But the only problem is we need to write the sign in a more compact form. And I'll show you in a minute how we're going to achieve that. So remember in my last video how we wrote the cosine in terms of exponential functions, and which was way easier to work with when we were doing calculus. So I want to use a similar strategy with the sine. So let's start with Euler's identity. So we have e raised to I theta being equal to cosine of theta plus I times the sine of theta. And then we take the negative of that, e raised to negative I times theta. Cosine of negative theta is just cosine of theta. Sine of negative theta is negative sine theta. So minus I times sine theta. Now instead of adding that like we did last time, why don't we subtract this equation from the top equation? So everything else becomes minus, this becomes a plus. On subtraction we have e raised to I theta minus e raised to negative I theta, and then the two cosines will just cancel out. We have I sine theta added with itself two times, so 2i sine theta. Why don't we divide both sides by 2i? So we obtain sine theta is nothing but e raised to I theta minus e raised to negative I theta over 2i. So that's a pretty compact definition of the sign in terms of these exponential functions, and let's plug that into our original problem. So now we can write I as the integral from 0 to pi over 2 of x divided by, instead of the sine of x we have e raised to ix minus e raised to negative ix divided by 2i, and then the 2i goes on top, you just flip it, dx. Now I don't really like these negative exponents, so we can convert them into positive exponents as follows. With x times 2i divided by e raised to ix minus 1 over e raised to ix dx, obviously. So we have a 2 outside, 2i actually, because if I is also a constant. Integral from 0 to pi over 2 of, well, we can cross multiply everything. We have x and then this goes on top times e raised to ix divided by e raised to ix multiplied by itself is e raised to 2ix minus 1 and a dx. Now this looks like a way easier form to work with, since we're going to be using integration by parts now. So we have a singleton x, so we are definitely going to only differentiate that, because differentiating that once will make it vanish. and then this entire other term, e raised to ix divided by e raised to 2ix minus 1. We're going to be integrating that. And for convenience, I'm going to find the antiderivative of this thing separately before we even go on to using the integration by parts formula. So let's do that on a fresh page. There's a lot to consider. So since we are going to be differentiating the x, let's just leave that because it's easy to find the derivative of just x. What we're concerned with actually is to find an antiderivative of e raised to ix divided by e raised to 2ix minus 1 dx. Just the antiderivative, we don't have a definite integral here. So now looking at the term in the numerator, we actually would like to use some substitution. So let u equals e raised to ix such that du is nothing but I times e raised to ix dx. So we can actually write our integral now. So we have e raised to ix dx on the top. So we have du over I is the numerator. So du and 1 over I can write outside divided by, this is e raised to ix squared, right? E raised to 2ix. So u squared minus 1. Now 1 over I is nothing but negative I, and we actually have a pretty neat formula for the antiderivative of u squared minus 1. So that's half times the natural log of u minus 1 over u plus 1. And I won't be writing the constant of integration because we don't actually need a constant of integration when we are doing integration by parts. And what was our u? We have to back substitute. We can't keep everything in u. What was our u? Our u was e raised to ix minus 1. So we have negative I over 2 times the natural log of e raised to ix minus 1 divided by e raised to ix plus 1. So since we're only going to be concerning ourselves with the antiderivative, I'm just writing that as it is separately. And now let's use our integration by parts formula. So we have 2i outside, and then we have the x is untouched. So x and times the antiderivative of what we're going to basically integrate, this other bit. So negative I over 2 times the natural log of e raised to ix minus 1 divided by e raised to ix plus 1. And remember that we have to evaluate that from 0 to pi over 2. And now we have to subtract by the integral from 0 to pi over 2 of the derivative of x, that's just 1, times the antiderivative of this thing, and we calculated that. So that's negative I over 2 times the natural log of e raised to ix minus 1 divided by e raised to ix plus 1 dx. And then I'm closing this bracket. Now we can actually multiply the 2i with everything that's inside the bracket. So the 2's are going to cancel out in both the terms. And we have negative I times I. So negative I squared. I squared is negative 1. So negative of that is just 1. So we have x times the natural log of e raised to ix minus 1 divided by e raised to ix plus 1, but evaluated from pi over 2 to 0 minus, well, negative I squared is positive 1, but we also have this negative outside, so a net negative of the integral from 0 to pi over 2 of the natural log of e raised to ix minus 1 divided by e raised to ix plus 1 dx. So we basically have two things now that we are going to have to evaluate. So this part I'm going to call I1, and this part along with the negative I'm going to call I2. So I is nothing but I1 plus I2. Fair enough. Let's do each of them on a fresh page. See you then. So we have I1 being defined as x times the natural log of e raised to I times x minus 1 divided by e raised to ix plus 1, but that's getting evaluated from 0 to pi over 2. So we are separately going to plug everything. So that's I1, sorry. So when we plug in pi over 2, we have pi over 2 as it is, then the natural log of e raised to I times pi over 2 minus 1 divided by e raised to I times pi over 2 plus 1 minus, when we plug in the 0, so we have 0 times the natural log of e raised to I times 0 minus 1 divided by e raised to I times 0 plus 1. So for now let's just write this as it is. Pi over 2 times the natural log of e raised to I times pi over 2 minus 1 divided by e raised to I times pi over 2 plus 1, and by virtue of this 0, and also although we're gonna have a 0 over here in the numerator of the log, you can actually estimate using limits and everything that this thing entirely is gonna go to 0. I'm just not showing all the steps now because this video is already gonna be long. So we have a 0, so we just basically ignore that. Now what is e raised to I over 2? E raised to I times pi over 2, sorry. Well, why don't we use Euler's identity for that? So we have e raised to I theta being equal to cosine of theta plus I times sine of theta. So now instead of theta, say we plug in pi over 2 such that we obtain e raised to I times pi over 2. We have theta is pi over 2, so cosine of pi over 2 plus I times the sine of pi over 2. If you know your trigonometry well, you know that if you know your trigonometry well, cosine of pi over 2 is 0, sine of pi over 2 is 1, so we have I times 1 plus 0. You can ignore the 0. I times 1 is just I, so e raised to I times pi over 2 is nothing but I. So we can directly substitute that now. So we have pi over 2 times the natural log of, instead of this thing we have I minus 1 divided by I plus 1. But let's convert this into a single imaginary number. We don't like this imaginary number in the denominator. So why don't I multiply and divide by the conjugate of this thing, of the conjugate of the denominator, that's I minus 1 and then I minus 1 here as well. So that's directly equal to pi over 2 times the natural log of, well, it's basically squared, so we can multiply every term by every term uh, using the associative property basically. So I squared minus 2 times 1 times I, which is an I, plus 1 squared, which is 1, and divided by I squared minus 1 squared. So that's going to be pi over 2 times the natural log of I squared is negative 1, and this positive 1 is going to cancel out. You have negative 2i divided by I squared is negative 1 minus 1 is negative 2. So we have pi over 2 times the natural log of 1. We don't need the absolute values now. But what's 1? We can just refer back to our Euler's identity to know that I is nothing but e raised to I times pi over 2. And from that, using some log properties, we can pull down the power to have I times pi over 2 times a pi over 2 of the power times the natural log of e. The natural log of e is 1. And over here we have I times pi squared over 4. The two pi over 2's get multiplied with each other. So what was this? This is basically our first part, our I1. It's time to do our I2 now. And that's going to be really long and really interesting. So stay tuned, guys. See you on the next page. So what was our I2? Well, we chose to include the negative also. So we have the integral from 0 to pi over 2 of the natural log of e raised to ix minus 1 divided by e raised to ix plus 1 dx. And now we can suck up the negative and then flip the argument of this natural log. So the integral from 0 to pi over 2 of the natural log, now I'm flipping the argument, e raised to ix plus 1 divided by e raised to ix minus 1 dx. Now instead of using the positive exponents, I'm going to be using negative exponents now, and you'll see in a minute why. So we have the integral from 0 to pi over 2 of the natural log of 1 over e raised to negative ix plus 1 divided by 1 over e raised to negative ix minus 1 dx. And we can do our good old fashioned cross multiplication now. So we have the natural log of 1 plus e raised to negative ix divided by 1 minus e raised to negative ix, and the denominators of both the things are constant, so those things get cancelled out in the ratio dx. But I would also like to remind you of a very, very nice fact, and that's actually the key observation in the entire question, if you ask me. And the observation is the inverse hyperbolic tangent of x is equal to half of the natural log of 1 plus x divided by 1 minus x. And looking at the form of the natural log over here, we have 1 plus a variable divided by 1 minus the same variable. So we can actually convert this into one of these forms, and you'll see why we are actually converting it into this form, because it gets really, really easy to evaluate after a point of time. So let's do that. So we have I2 now, and we're going to be using this identity, the integral from 0 to pi over 2 of, well, we had half, so we can multiply and divide by 2, half and a 2 to maintain equality. So we have 2 times the integral from 0 to pi over 2 of the inverse hyperbolic tangent of not x but e raised to negative ix, because that was the entire variable that was satisfying this identity, right? And a dx. Now the use of writing e raised to negative ix inside a hyperbolic tangent, inverse hyperbolic tangent actually. Well, because now we have a specific function that's dictating how everything is going to occur. And one thing about specific functions is that we can use Taylor series of them to calculate absurd integrals like these. So the Taylor series for the inverse hyperbolic tangent, the tangent inverse of x, is basically the sum from n equals 0 to infinity of x times 2n plus 1 divided by 2n plus 1. So we can definitely use this fact now. So I2 is going to be 2 times the integral from 0 to pi over 2 of the sum from n equals 0 to infinity of not x but e raised to, because that's the argument, negative ix, the whole thing raised to the 2n plus 1th power divided by 2n plus 1. And definitely do not forget the dx. Well, I'll like to bracket this term. Now we can assume uniform convergence. So that we can interchange the sum and the integral. So we have 2 times the sum from n equals 0 to infinity. I'll take all the terms that only have an n outside. So 2n plus 1, 1 over 2n plus 1 basically. And the integral from 0 to pi over 2 of e raised to x, and everything is outside. So negative I times 2n plus 1 is basically like a constant term outside, a coefficient term outside. So integrating that, we obtain 2 times the sum from n equals 0 to infinity of, we have 1 over negative I, that becomes a positive I in the numerator. And then we have also this term 2n plus 1. So 2n plus 1 times 2n plus 1 is 2n plus 1, the whole thing squared. And then the exponential term is untouched, e raised to negative ix raised to 2n plus 1th power. But we still have to evaluate that from 0 to pi over 2 because it was a definite integral. So now we basically have 2i times the sum from n equals 0 to infinity. When we plug in pi over 2, we have e raised to negative I times pi over 2. And why don't we use our Euler's formula again, Euler's identity again. So we have e raised to I theta is cosine theta plus I times sine of theta. So for theta equals negative pi over 2, we have exactly what we obtain when we plug in pi over 2 over here. So that will get rid of the cosine. Cosine of negative pi over 2 is 0 still. And the sine of negative pi over 2 is negative 1. So we have negative I now. So negative I raised to 2n plus 1 divided by 2n plus 1, the whole thing squared, and the second term minus 2i times the sum from n equals 0 to infinity of 1 to the 2n plus 1, because when we plug in 0 we obtain a 1, right? E raised to 0 is 1, divided by 2n plus 1, the whole thing squared. Okay, great, we have two terms. Now what are we going to do? Now I'll also want to remind you of another fact. So basically the great fact is, say we have a function of x being defined as the sum from n equals 0 to infinity of x to the 2n plus 1th power divided by 2n plus 1 squared. This is nothing but the integral from 0 to x of the inverse hyperbolic tangent of, say, a dummy variable t divided by t dt, which is equal to half of the dilogarithm of x minus the dilogarithm of negative x. And why is this useful? Because look at our two sums. They're in this form. They're in the original form of f of x, x to the 2n plus 1 power divided by 2n plus 1 squared. So for the first term we have f of negative I, and we have f of 1 for the second term. So let's just use this its relation, or the relation of f of x with the dilogarithm function, to see where we'll end up exactly. So we have I2 now being equal to 2i outside of half of the dilogarithm of negative I, because we have a f of negative I, minus the dilogarithm of negative I, or positive I, and minus half of the dilogarithm of 1 minus the dilogarithm of negative 1. So now in all the terms the 2.5 cancel out. We just have an I being multiplied out everywhere. So we have I times the dilogarithm of negative I minus I times the dilogarithm of I minus I times the dilogarithm of 1 plus I times the dilogarithm of negative 1. So we are going to be keeping the first two terms as they are. I times the dilogarithm of negative I minus I times the dilogarithm of I minus I times, what's the dilogarithm of 1? Well, that's the Riemann zeta of 2, right? And that's pi squared over 6. And what's the dilogarithm of negative 1? Well, that's the negative of the Dirichlet eta of 2, which is pi squared over 12 basically. So first two terms as they are, I times the dilogarithm of minus 1 minus I times the dilogarithm of 1, and when I add these two things up, I have negative I times pi squared over 4. Well, fine, we're going to be ending our process of I2 here, and it's time to recombine I1 and I2 together to constitute I again. So I, as previously suggested, was I1 plus I2. And what was I1? I times pi squared over 4, right? And what was our I2? Which was I times the dilogarithm of negative I minus I times the dilogarithm of I minus I times pi squared over 4. And the best part of today is these two crazy imaginary terms cancel out. We only left with I times the dilogarithm of negative I, negative I times the dilogarithm of I. Now just for the sake of simplification, if we were to write it in the form of our f of x, we will have negative 2i times the sum from n equals 0 to infinity of I times 2n, I raised to 2n plus 1 divided by 2n plus 1, the whole thing squared, which on simplification will be 2 times the sum from n equals 0 to infinity of I times 2n plus 1 times 1 times 2n plus 1 divided by I basically took the negative I in the denominator. We always have a 2n plus 1, the whole thing squared over here. So now one of these i's are going to cancel out, and we have I squared raised to n. And what's I squared? It's negative 1, right? So we have 2 times the sum from n equals 0 to infinity. 1 raised to any power is just 1. We're going to be having negative 1 to the n power divided by 2n plus 1, the whole thing squared. And what's this part? That's right, it's Catalan's constant. So we have 2 times g, where g is Catalan's constant. So that's a pretty result. I mean, some of you who watched my previous innocent integral video of x over cos of x would recognize this form immediately as being twice of the Catalan's constant. But you know, it's really fun that Catalan's constant has all these other different forms. So basically, to simplify what we learned in today's video, we had a problem I, defined as the integral from 0 to pi over 2 of x divided by sine of x dx, and that where we simplified sine of x using the exponential definition of the sine. Then we used integration by parts. We obtained two different things. We evaluated the first part directly by plugging in pi over 2 and 0. We converted the second part into an inverse hyperbolic tangent function. We used the Taylor series. We got two infinite series after plugging in the upper and lower bounds. We used our previous knowledge of the integral from 0 to x of inverse tangent of t over t dt to get the difference of two dilogarithm functions. Well, one of them just cancelled out with I1, and then finally we got a part which we simplified to be 2 times Catalan's constant. So 2 times Catalan's constant, or 2 times the sum from n equals 0 to infinity of negative 1 to the nth power divided by 2n plus 1, the whole thing squared. So that's a really beautiful result, very neat. And I'm afraid that's all for this video, guys. So please like, share and subscribe. Recommend my channel to all of your number file friends or those who actually want to learn something in math. Stay in, stay safe. Peace out. Have a great day.